March 1944, Recklinlatz Airfield, Mecklenburg, Germany. The systematic examination of captured enemy aircraft had become a critical function of the Luftwaffe's Technical Intelligence Service. At Airprobung Stella Rechlin, the Reich's primary aircraft testing and evaluation center, teams of engineers and pilots worked to understand every advantage the Allies possessed in the air war. What they discovered in the early spring of 1944 would fundamentally alter their understanding of American industrial capacity and the future of the air war over Germany. The captured P-51 Mustang arrived at Rechlin on March 6, 1944. Transported by rail from a crash site near Brandenburg, the aircraft had been shot down 2 days earlier during the first American fighter escort mission to Berlin. The pilot had not survived the impact, but the airframe remained largely intact, providing German technical staff with their most complete example yet of the aircraft that was rapidly changing the balance of air power over the Reich. Schmann von Bombach, who served in aircraft development and would later command Kampfgeschwadertund, oversaw the initial examination. The young American pilot's navigation charts, still in the cockpit, showed the route from an airfield at Debden in England to Berlin and back, a distance of over 0 mm round trip. The technical evaluation began immediately. German intelligence had been tracking reports of increased American fighter activity deep over German territory, but the official assessment remained that single-engine fighters lacked sufficient range to escort bombers to Berlin. The distance from English bases to the German capital measured approximately 460 km one way. Standard fighter aircraft, even with external fuel tanks, could not carry enough fuel for such a mission while maintaining combat capability. This assessment had been based on analysis of earlier captured P-47 Thunderbolts and P-38 Lightnings, both of which had demonstrated limited penetration into German airspace before fuel constraints forced them to turn back. The events of March 4th and 6th, 1944 had shattered these assumptions. On March 4th, P-51 Mustangs from the 4th Fighter Group, flying their first mission in the new aircraft after transitioning from P-47s just days earlier, had escorted a small bomber force to Berlin. Weather and communication problems limited the effectiveness of this first mission, with only 32 bombers reaching the target. But the significance was unmistakable. American single-engine fighters had reached Berlin, engaged in combat, on return to England. Days later, on March 6th, approximately 660 bombers attacked Berlin in daylight, escorted by over 150 P-51 Mustangs along with P-38 Lightning and P-47 Thunderbolt groups. The escort fighters engaged Luftwaffe interceptors over the German capital and accompanied the bombers home. This was not a fluke or a one-time penetration. The Americans had solved the escort fighter problem. General Major Adolf Galland, General de Jagdflieger, and one of Germany's most successful fighter aces with over 100 victories, had flown combat missions during this period despite his administrative position. He encountered P-51 formations over Germany and immediately recognized the implications. His combat assessments submitted through official channels noted that American fighters were operating at full combat capability over Berlin, engaging aggressively with no apparent fuel conservation behavior. They were not flying at the limits of their range. They had reserves. This contradicted everything Luftwaffe intelligence believed about American fighter capabilities. Galland's reports emphasized the P-51's superior performance at high altitude, where it outmatched both the Messerschmitt Bf-109 and Fowler-Wolf FW-90 in speed and maneuverability. Above 20,000 ft, the technical examination at Rechlin focused first on determining how the Americans had achieved this range. The evaluation team measured the P-51B's internal fuel capacity, The aircraft featured 2 wing tanks, each holding 92 gal of aviation fuel for a total of 184 gal in the wings. Additionally, the fuselage contained an 85 gal fuel tank positioned directly behind the cockpit. This fuselage tank had been a relatively recent addition to the P-51B design, incorporated during production to extend range. Total internal fuel capacity was 269 gal. The Packard-built Merlin engine, a licensed produced version of the Rolls-Royce Merlin that had transformed the Mustang's high-altitude performance, consumed fuel at rates that varied with power settings. At economy cruise settings, the engine burned approximately 60 gal-hour. At normal cruise power, consumption increased to approximately 75 gal-hour. German engineers performed range calculations using these figures. With 269 gal of internal fuel and consumption of approximately 70 gal-hour at cruise settings, the P-51B could fly for roughly 3.8 hours. At the aircraft's cruising speed of approximately 300 mph, this yielded a maximum range of 1,140 mph. This was precisely enough to reach Berlin from English bases and return, but only barely, with no reserves for combat operations. Yet, combat reports clearly indicated the American fighters had engaged in prolonged dogfights over Berlin, sometimes lasting 15 to 20 minutes before disengaging and flying home. Combat power settings consumed fuel at rates exceeding 100 gal, and such fuel expenditure should have left the aircraft unable to complete their turn journey. The calculations did not explain what German pilots were observing in combat. The answer became apparent when technical staff examined the aircraft's wing structure more carefully. The P-51B featured standardized hardpoints under each wing designed to accommodate external stores. These attachment points included fuel line connections, indicating they were designed specifically for external fuel tanks. Drop tanks were not a new concept. German fighters had used them since the Battle of Britain. The Bf-109 could carry a 300L drop tank. The FW-190 regularly employed them for extended range missions. Drop tanks allowed aircraft to carry additional fuel externally, then jettison the empty tanks before entering combat to reduce weight and drag. This was standard practice for all air forces. The question was not whether the Americans are using drop tanks, but rather what capacity these tanks had and how the Americans were producing enough of them to maintain operational tempo. The search for American drop tanks from the March missions began immediately. Intelligence. Officers plotted likely jettison points based on the engagement locations reported by Luftwaffe. Pilots' drop tanks would typically be released when enemy fighters were encountered as the external stores. Reduced maneuverability and speed search. Teams composed of Wehrmacht personnel and Hitler Youth volunteers spread across the countryside northeast of Berlin looking for any debris from the air battles. Within 3 days, several objects were recovered from fields and forests in the region. Most were fragmentary, crushed on impact or damaged by the fall. But 2 examples arrived at WWII in relatively intact condition, having landed in soft soil or winter wheat that cushioned their impact. The captured drop tanks revolutionized German understanding of American industrial methods. The tanks were cylindrical, measuring approximately 108 in length with a diameter of roughly 22 in at the widest point. Capacity calculations indicated each tank held approximately 108 US gal 400L. 2 such tanks would provide 216 additional gallons of fuel, extending the P-51's total fuel capacity to 485 gal. With this fuel load, the Mustang could fly for approximately 6.7 hours at cruise power settings, yielding a range exceeding 2,000 km. This was more than sufficient for the Berlin mission with substantial combat reserves. The fuel capacity mathematics now made sense. But what captured the immediate attention of German engineers was not the capacity of the tanks, but rather their construction. The drop tanks were not made of metal. Running a hand along the surface revealed a texture unlike aluminum or steel. The silver paint coating the exterior could not disguise the fundamental nature of the material beneath. When engineers carefully scraped away a small section of the paint near the tail cone, they found multiple layers of heavy paper, each layer perhaps half a millimeter thick, compressed and laminated together with a Rainus adhesive. The construction was sophisticated and purposeful. The nose cone and tail cone were formed from overlapping pieces of the paper material pressed into shape like papier-mâché. Each piece was visible as a slight ridge where it overlapped with adjacent piece, creating a scalloped texture. The center section was seamless, wrapped around a cylindrical form in continuous layers. The fuel fittings were brass, precisely machined and properly sealed. Peering through the filler cap revealed an interior coated with what appeared to be cellulose-based lacquer designed toruses, the corrosive effects of aviation gasoline. German material specialists were brought in to analyze the tank's construction in detail. The paper was identified as kraft paper manufactured using a chemical pulping process that produced exceptionally strong cellulose fibers. This was the same material used for heavy-duty shipping containers and industrial packaging. The adhesive proved to be a resource null formaldehyde resin, a thermosetting polymer that created bonds stronger than the paper itself when heat cured. The lamination involved at least 12 separate layers of paper, each one carefully oriented to provide strength in multiple directions. Anti-slush baffles made of wood were installed inside to prevent fuel from surging during maneuvers. The entire construction process was clearly standardized and designed for mass production. Most significantly, the empty tank weighed approximately 80 lb compared to 65 to 75 lb for a comparable metal tank of smaller capacity. The paper construction was not significantly lighter than metal, but it offered other advantages. The implications were immediately clear to the technical staff at WWII. The Americans were manufacturing fuel tanks from non-strategic materials. Paper and wood-based resins did not require the aluminum, steel, or other metals that were increasingly scarce in wartime economies. The manufacturing process required no specialized metalwork equipment, no skilled metal workers, no welding or forming of sheet metal. These tanks could be produced in any paper mill or packaging factory with relatively simple modifications to existing equipment. The United States had hundreds of such facilities. If even a small percentage of American paper production had been converted to drop tank manufacturing, output could reach thousands of units per week. The tanks appeared to have no serial numbers, no manufacturer markings, nothing to indicate limited production. They were commodity items, mass-reduced and completely expendable. Intelligence officers began researching American paper industry capacity. The United States produced approximately 12 million tons of paper annually before the war, with production increasing during wartime mobilization. Converting even 1% of this capacity to drop tank production would yield over 100,000 tanks per month, far exceeding any plausible requirement for P-51 operations. The real constraint would not be materials, but rather the availability of manufacturing equipment and labor to assemble the tanks. But this was precisely the type of manufacturing that could be performed by semi-skilled workers after minimal training. The paper tanks represented industrial efficiency and resource optimization on a scale that German planners found difficult to comprehend. Further, analysis revealed additional details about the paper tank's design and use. The tanks were strictly single-use items. The resourceful adhesive, while creating strong bonds when cured, was slowly dissolved by prolonged contact with aviation gasoline. Intelligence. Reports and interrogation of captured American aircrew indicated that paper tanks had to be filled immediately before flight and could not be stored filled for more than a few hours without developing leaks. This was not a limitation that affected operational use. Fighters were fueled as part of their pre-flight preparation. The tanks would be used for a few hours during the mission, then jettisoned. This loose nature actually simplified logistics. There was no need to recover and reuse the tanks. No need for cleaning, inspection, or maintenance. They were expendable by design. The German evaluation also noted the color coding of the tanks. Paper drop tanks were painted silver, while metal tanks used by American forces were painted gray. This color distinction allowed ground crews to quickly identify tank types during fueling operations. The silver finish on paper tanks also helped reflect solar heat, reducing fuel evaporation and vapor pressure issues at altitude. Every aspect of the design reflected systematic engineering optimization for mass production and field use. By late March 1944, German intelligence had traced the origin of the paper drop tanks to British development. The Air Ministry in London had commissioned development of impregnated paper fuel tanks in 1943 to conserve strategic metals, particularly aluminum. The Bowater-Scott Corporation, utilizing expertise in paper manufacturing, developed the production process. The tanks entered service with RAF fighter squadrons in late 1943. American forces quickly adopted the design, with multiple manufacturers in both Britain and the United States producing tanks for use by USAF fighter groups. The innovation had been driven by British resource scarcity, but was being exploited on a massive scale by American industrial capacity. The broader implications extended far beyond fuel tanks. German technical staff began a systematic review of captured American equipment, looking for other examples of industrial innovation and mass production techniques. The results painted a consistent picture. American equipment was not always technologically superior to German equivalents in terms of individual component performance. German optics were often better. German small arms were often more sophisticated in design. German armor metallurgy was in some respects more advanced, but American equipment was consistently better manufactured, more standardized, more reliable, and available in vastly greater quantities. The American approach prioritized producibility over perfection. Components were designed from the outset for mass production by semi-skilled workers using standardized tooling. Parts were interchangeable between units without hand fitting. Assembly line methods reduced production time and increased output. The contrast with German production methods was stark. German weapons and equipment were often technical masterpieces hand-fitted by skilled craftsmen. A German tank or aircraft engine represented the peak of precision engineering, but building such equipment required skilled labor, specialized tools, and significant time per unit. Production rates were constrained by the availability of master craftsmen and precision manufacturing equipment. The Germans built superior individual items. The Americans built adequate items in overwhelming quantity. In industrial warfare, quantity had proven decisive. Analysis of P-51 Mustang production illustrated this principle. North American Aviation had designed the original Mustang prototype in response to a British requirement in 1940. The prototype NA-73X was completed just 117 days after the contract was signed, one of the fastest design-to-prototype cycles in aviation history. The first flight occurred on October 26, 1940. By 1944, North American was producing P-51 variants at 2 facilities. The Inglewood plant in California averaged approximately 364 Mustangs per month during peak production periods. The Dallas plant contributed additional production. Combined output across both facilities reached an average of approximately 574 P-51s per month during 1944, with production accelerating throughout the year. Peak monthly production would reach 881 aircraft in January 1945. Each P-51 required approximately 15,000 individual parts manufactured by hundreds of subcontractors across the United States. The Packard-built Merlin engines were produced in Detroit rates exceeding 300 units per month. Final assembly of a P-51D required approximately 22,000 man-hours of labor, but the production line system meant that completed aircraft rolled out of the factory at intervals of a few hours. At peak efficiency, a new Mustang was completed approximately every 2 hours. The scale and efficiency of this production system exceeded anything Germany had achieved. Messmith and Fowler-Wolf combined produced approximately 600 fighters per month in early 1944. Despite operating under emergency priority programs and utilizing forced labor, German aircraft production could not match American output. The resource implications were equally sobering. American aluminum production in 1944 reached approximately 1.25 million tons, equivalent to 2.5 billion pounds annually. This represented a massive increase from pre-war production of approximately 164,000 tons in 1939. Germany's aluminum production, by contrast, peaked at approximately 250,000 tons per year and was declining due to bombing of production facilities and loss of bauxite sources. The Americans had approximately 10 times Germany's aluminum production capacity. The decision to manufacture drop tanks from paper rather than aluminum was not driven by metal scarcity. The United States had sufficient aluminum to produce every drop tank in metal, if desired. Paper was chosen because it was cheaper, required less critical manufacturing equipment, freed aluminum for other uses, and could be produced more quickly with less skilled labor. This was optimization, not desperation. The psychological impact of these revelations spread through the Luftwaffe technical and operational communities. The paper drop tank became a symbol of American industrial capability and the fundamental disparity in resources between the combatants. Captured examples were displayed at technical briefings for Luftwaffe personnel. Pilots transitioning to fighter units were shown the tanks and asked to calculate the implications for combat tactics. The message was clear. American fighters could now escort bombers anywhere in Germany. The previous defensive strategy of waiting for Allied fighters to reach their fuel limits and turn back was obsolete. Luftwaffe fighters would have to engage the escorts to reach the bombers, and those engagements would cost aircraft, and pilots at rates Germany could. Galland provided the operational assessment. In conferences with senior Luftwaffe leadership throughout the spring of 1944, the P-51 was superior to German fighters above $20,000 foot, he emphasized repeatedly. It was faster than the Bf-109 at altitude and more maneuverable than the FW-190 with the extended range provided by drop tanks. It could escort bombers throughout their mission profile. German fighters could no longer attack bomber formations unopposed after Allied escorts turned back. Every intercept now required fighting through the fighter screen. Loss rates were climbing steadily. In January 1944, the Luftwaffe lost approximately 90 fighters, while claiming approximately 150 Allied aircraft destroyed. By February, German losses had increased to approximately 160 aircraft against approximately 230 Allied losses. The trend was clear and unsustainable. The Americans and British could replace losses faster than Germany could inflict them. The summer of 1944 brought the full impact of American escort fighter capability. The 8th Air Force conducted deep penetration raids almost daily when weather permitted. Mustangs provided continuous escort from England to targets across Germany and back. Luftwaffe fighter losses mounted catastrophically. In June 1944, approximately 350-day fighters were lost defending the Reich. In July, losses exceeded 350 single-engine fighters in the West alone, representing a 31.2% monthly attrition rate. August saw similar losses with a 36% attrition rate,